So today we're going to be talking about graphing motion, and specifically it's linear motion. So the first thing that I want to do is start off with a story of the Three Little Pigs. So many of you guys already know this, but essentially we have these three pigs. One pig builds his house out of straw, right? It's very weak. Not made of much. He was kind of lazy. He just wanted to chill, have the easy life. But that's not good, right? So he's just kind of chilling here. He's waiting around. He's all good, right? Next, we have another pig. Builds his house out of sticks. It's kind of like a large cabin. Right, maybe it looks something like this. There's even a little doorway there. Right. Slightly stronger, but still, this guy was also feeling a little bit lazy, didn't want to do too much. And so, it's a little stronger than the straw, but not too strong. Lastly, we have another pig. He studied very hard, understood material engineering, and he made his house out of brick and, we'll just say for fun, synthetic materials. So he has, nice little house, maybe with a little chimney on top. Right, so we have these three little pigs, and they live in their houses. What ends up happening is there is a big bad wolf, right? There's a wolf that wants to eat these pigs. The wolf, he kind of doesn't really have a house. He kind of just wanders around. So we have this little wolf guy. I'm going to try to draw the best wolf that I can draw, but I'm not necessarily the best drawer in the world. So we have this wolf, right? And he's just going to be a little head with a stick figure. He sees that these pigs are making these houses, and he's hungry, right? He's hungry. So he's going to go to the first house, and he's going to huff and puff and blow this house down. So with the straw one, very easy to blow down. It just kind of gets knocked over and it dies. So next, the wolf goes to the stick house. It's not too far, so maybe he's just going at a pretty constant pace, just jogging there. The pig in the straw house had run into this house so that he could escape the wolf. So he gets there. The wolf again, he huffs and he puffs and he blows that house down. So this one gets knocked out. So now both the other two pigs, they go to their brother's house, and they hide in there. But the wolf, of course, follows along and tries to huff and puff and blow this house down, but he just can't do it. The house is too well made. And the real story, I think, this is my huffing and puffing of wind. He tries to climb into the chimney, and then the pigs have a boiling vat of water, and essentially he gets boiled alive and they eat him. But in our story, he's just going to give up and go all the way back home. So sorry, I forgot to do the stereo. He's going to go all the way back to where he started. Right? So what we're going to do is we're going to take a look at this story and we're going to graph it. And we're going to kind of use some physics terms maybe. So when he started, we're going to say that he underwent a constant acceleration. So he started off not running yet, but he woke up, and then he started moving, got a little bit faster, and then when he got to this pig's house, he stopped. So I'm going to use these three terms. I'm going to say constant distance, which is going to be our cx. Remember, this is kind of representative of displacement. So constant displacement, I guess. Constant velocity and constant acceleration. And all of these can be positive or negative, just depending. For us, our direction of positive is going to be towards the pig's house, and the direction of negative will be towards where the wolf started. So when we look at this, the wolf underwent a positive constant acceleration, and then he stopped. When he stopped to blow this house down, he was a positive distance away from his starting point, which is right here. So this is supposed to be my origin point. So he's a positive constant distance. Then we'll say that rather than accelerating this time, he was just jogging at a constant pace. So we'll give him a positive constant velocity. You might be asking, wait a second, if he goes from not moving to moving, doesn't he undergo an acceleration? Yes, he does. But for our case, and you'll see when we graph it now, you'll see why I did it this way. So then he gets to the next house, huffs and puffs, blows that house down. We have a positive constant distance. We'll say for the next one, he's again going at a constant rate. However, it's faster. So he's definitely going a lot faster. So this one's definitely bigger than the other one. Again, he huffs, puffs, tries to blow that house down, but it doesn't work. And then eventually, as he's on his way back home, he runs all the way back, so he's going to have a negative constant velocity. So what we're going to do is we're going to kind of graph these in various different graphs, essentially. So our first graph we're going to look at is a distance or displacement versus time graph. So displacement versus time. So we're going to graph this entire story. So it's going to be a little bit long. Right, so let's keep in mind, as we go upwards on the y-axis where our displacement is being graphed, he's getting further from his starting point. Remember, as we go further to the right on the time, obviously time is passing. Remember that we don't want to ever have any vertical asymptotes because that means we're in infinite amounts of positions at one time, like we're teleporting, which doesn't make sense. So let's begin. So the wolf starts right here at the origin point and undergoes a constant acceleration. So it gets faster and faster and faster. And what that kind of means is that the distance that he travels gets greater and greater and greater over time. So what that's actually going to look like is a curve. So it's going to go something like that. And then he stops. When he stops, right, it's going to look like this because at this point, let's say, I don't know, maybe this is like 10 meters away. As he's huffing and puffing, if he's not moving, then he's a constant 10 meters away from his home, from his starting point. Then let's say he starts moving at a constant velocity. We're moving at a constant velocity. That means you're traveling the same displacement over the same amount of time. So that's going to be a really smooth slope for us. So it's going to look maybe something just like that. And this is supposed to be a straight line. I'm going to make this a little bit more less steep. So he keeps going, keeps going, keeps going. And then he eventually gets to this other pig's house and he stops moving again. Right? So maybe we could say that this is about, I don't know, 15 meters. And I'm just trying to use these numbers to kind of give you an idea of like how we're graphing. All this is just on a relative scale. So again, the big bad wolf goes to the next house, but this time he's like running. He's still going at constant speed, but he's running really fast. So we're going to give this a steeper slope. It means he's covering a greater distance in the same amount of time, or just in shorter amounts of time. So it's going to be a little bit steeper here. So notice that this one right here is less steep than the one we just drew. And then again, he huffs and he puffs and he tries to blow the house down. This is supposed to be a horizontal line. And then he gives up and he just goes home with a constant velocity. Well, if he's going home with a constant velocity, that means he's going first at a constant pace, but he's pointed in the negative direction. And so that's going to be us going back to our starting point. Right? And our starting point on the x-axis is not actually here, right? Because time has passed, right? We're not going back in time. We're only going back to our original starting point, but still moving forward in time. So our graph will kind of just go all the way back here. This is, again, supposed to be a straight line, but my hand, obviously, not perfect. So we have something that looks like that. If we were to graph this, right, and label everything, we have a positive constant acceleration, constant displacement, positive constant velocity, positive constant displacement, a faster constant velocity. So I'll draw that V a little bit bigger. Another positive constant displacement, and then a negative constant velocity. So what we just did here is we're looking at a displacement versus time graph, distance versus time graph, and we can see kind of how this all was changing. And so actually, sorry, I should be more specific. This is a displacement versus time graph. On a distance versus time graph, no matter which way the wolf would go, he would, of course, increase in his distance. So this is a displacement versus time graph. So sorry that I've been using those interchangeably. Next, let's do a velocity versus time graph of the exact same situation. So now we're trying to graph his velocity. So this is different from your displacement. As we go up on the y-axis, that means we're increasing our speed. Time works the same way. We're always moving in time. So think about it this way. A constant acceleration is a smooth, constant change in velocity. And so what that's going to give us to start off is an angled line. Now if we stop moving, right? If we stop moving, how fast are we going? Well, we're not going fast at all. So it actually drops, right? And this is where you're going to hate me because I just told you no asymptotes. Right? It's going to drop like that. In real life, instead of looking like this, it would look more like this and round down. But I just want you to be able to identify the different parts of the graph. So I'm going to make this a little bit unrealistic. So we have this, and then he has a constant velocity. Now it's not too fast, so what we're going to do is we're going to accelerate, right? And then we're going to move over time at a constant velocity. And if we were to graph this, maybe we'd say he's moving at like 3 meters per second. Right, so if he's moving at a constant 3 meters per second over time, that gives us a horizontal line. So he does this for a good while, maybe about right there, and then he stops moving again. If he stops moving, well, that means he's back on the x-axis where our time is, because he's traveling 0 distance over time. He has 0 meters per second of velocity. So he does that for a certain amount of time, stays right on there, and then this time he has a faster velocity, positive constant velocity. So if it's faster, maybe we get something that looks like that. And then again, that drops. He stops moving. He's huffing and puffing, trying to blow this brick house downwards. Right, and then finally, last but not least, he goes home. Well, if he's going home, going in the negative direction, what does that mean? But he is now underneath our x-axis until he gets home, and eventually he gets home. If he stops moving, we could end it right there. So when we look at this again, we have a positive constant acceleration. Down here, just looking at the graph, you actually can't tell if it's a positive or a negative constant distance. So the most that we can describe, the most that we can say, is a constant displacement. I meant to say displacement, my bad. So for something that you may notice is that as we do higher level orders of graphs of distance, velocity, and acceleration, we lose some description. For here, we could tell that it was positive because it was in the positive direction of our axes. Next one, we have again a positive constant velocity. Again, we have down here, he huffs and puffs and tries to blow the stick house down, or he does blow the stick house down. Then he starts running. Another higher constant velocity. Huffs and puffs, tries to blow the brick house down, but then gives up. And then as he goes home, we have a negative constant velocity. So I hope you can kind of see what's happening here, but I'll make it more specific in a second. Last but not least, we have an acceleration versus time graph. And this is going to be more often than not the most simple of graphs, because there's only so many things that you can graph. So initially, he starts with a positive constant acceleration. So let's just say his acceleration was 1 meter per second squared. Right, so if he starts up there, then that goes on for a while. And then he has a constant distance. Well, if he has a constant distance, he's not accelerating. So we drop down to a 0 acceleration, which is down here. And here's the fun part. If you have a constant velocity, you're also not accelerating. Right? So if you're not accelerating, if we look at the rest of the graph, it's either velocity or constant velocity or constant distance. That means for the rest of this, we're on this x-axis because we're never really accelerating. So if we're just looking at these in parts, right? So we have like a little subsection here. We have one here. And I'm matching them from the graph above, by the way. We have one about here. We have one about here. So if we're just looking at all these separately, right, and this actually goes on to over here, and we were to start labeling these, well, the first one we can actually say is positive constant acceleration. Down here, and for the rest of it, we don't know if it's constant velocity or constant displacement. And moreover, plus or minus, we're not even sure. So we can't really tell. So what's nice is that we can graph acceleration more nicely, but we lose description. And so I hope this kind of story helps you kind of look at like what motion graphs are, what they represent.